The usual way in which we learn a word model, that is a model of the environment in model-based reinforcement learning, is not scalable at all. Why? Well, it has to predict every single pixel of the next observation. But also the deep neural network that we use to approximate the environment has a finite capacity. So we cannot model the entire world. But do we need to? For example, in a self-driving car, we don't need to predict everything. We only care about a small portion of the environment. For example, predicting or forecasting the trajectory of the people, of the cars, or the position of the traffic lights, and so on and so forth. So why learning everything from the environment where only a small part of it will be very useful for the downstream tasks? This is also how people learn the environment. We are learning in a goal-directed way, and only those spaces that are useful for accomplishing a task. Everything else doesn't matter. But because we are learning the word model in a self-supervised way, that is without knowing the real reward from the environment, it's not easy in the first phase where we learn the word model to distinguish what part of the environment can be useful and to learn them versus all the other that are not useful for all the downstream tasks. The paper that we are talking about today, goal-aware prediction, learning to model what matters, has a solution to this problem. And as the title say, they created an algorithm that learn a word model only of what matters from the environment, and everything else is discarded. But remember that we are in a self-supervised settings. We don't know the reward function, and so we have to learn only what matter without knowing the downstream tasks. In this video, we'll see the solution proposed by the paper, how does it perform on some toy tasks, and see if it's scalable to real-world solution, where we potentially have an infinite number of complexity and corner cases. So let's first see the usual architecture for our word model. But remember also to subscribe and like the video if you want to see more content like this. So our word model. The usual structure is this. We have an encoder-decoder that tries to learn a latent space for the current state that we call Z. We have obviously an encoder, an decoder, and then a transition model, that is the dynamic model, that from the current latent space predict the next one. And this is built in such a way that from the current image, we can predict the next image or the next state of the environment. And you can see that the model doesn't have a cognition of what the most relevant part of the environment are. It just learns everything, every single pixel from the current and the next state. And this is the solution proposed to only learn what matters from the environment. And what they propose is to learn a goal condition dynamic model and predicting just the residual. So what this means is that the model is aware of the goal you want to reach. And you can see that it has two inputs, the current state and the goal state, that is the final state of the trajectory, and it predicts just the difference between the goal and the current state. But the overall architecture is the same. We have an encoder and decoder and a forward dynamic model that tries to predict from the current latent space the next one. But the nice thing of this solution is that now, because we are a model aware of the goal and predicting just the residual that they call goal state residual, everything else that is not useful for the goal is not encoded, embedded in the neural network. So this means that the task is much easier to learn. So for example, if we are in a real world setting where we have to control a crane. With this solution, we can just build a model of the crane and discard everything else that is in the background. And the other important thing about this solution is that now the model is biased toward the solution. And what I mean by that is that, for example, if this axis is the distance towards the goal, and this is the difficulty of the prediction of, for example, the mean square error between the state goal and the current goal, we'll see that as we approach the goal, the mean square error will decrease, because now we are predicting the difference between the state goal and the current state. So this approach to zero when you are very close to the goal state. You can see that, for example, here everything is black. And this means that the model will be biased toward directing the prediction toward the solution. But remember that we are now in a self-supervised setting. We don't know the final reward function. And this means that we don't have the goal state. So how to do it? Well, in the paper, they exploit a solution proposed many years ago in another paper that is called Hindsight relabeling or goal relabeling. They just take some fictitious trajectory, for example, this one. This is the state S0, and this is the last state. And what Hindsight relabeling does is just take this state as goal state, so we'll call as G, and this one as starting state. So you can see now that if we're going back to our image, here the goal is just the last state of a trajectory. In this way, we can trick the neural network, think that that is the real task that we want to achieve. In this way, we can run a random policy for an episode and collecting all those states seen during the trajectory, take the start state and the goal state, and then predicting this word model that I just explained. So now we have the big question: does this really works? And to answer this question, we have to decompose it in 3 different parts. And so what we expect to see is to have lower errors on good and relevant state of a trajectory and an average error all the other states. The second thing is that we want to see an improvement on the downstream tasks, meaning that it actually helps to learn better the ultimate task that we want to learn. And the third one is that we want to see if this solution scales to arbitrarily large problems. They tested the algorithm on this environment where they have 4 different tasks. And the tasks are all about moving an object from a position to another one, or moving 2 objects, or opening and closing the door with some abstraction in a form of blocks. And in these plots, you can see the appellation study on their algorithm, on the same algorithm without the conditioning on the goal, and the red one is without the residual. They evaluated the error on 1000 trajectories on a held out dataset. You can see that their approach, the full approach, reaches the same performances of all the others. But if you move towards the best trajectories, here the best 100 and here the best 10, you can see that the gap is widening, and their full approach, the blue line, reaches a lower mean square error, showing that their algorithm really learns what matters, better fitting the states that allow it to accomplish a task. And to answer the second question, that is, see if this solution really improved the downstream tasks, they tested the gap versus 3 other algorithms, that is a standard latent dynamic model, that is Planet, an inverse model, and a model-free approach. Their approach indeed performed better than all the others, meaning that it really improves the accuracy of those states that actually allow it to accomplish the goal. And by the way, for planning, they use a model predicting control in the latent space of the model. Lastly, to see if gap scaled to real-world images, they applied their algorithm on stochastic video generation algorithm on a video prediction task. And you can see here, for example, the prediction of the ground truth of the standard stochastic video generation, and this is SVG with gap. You can see, for example, that the solution with gap encodes the image and predict the next state much better than the SVG version. For example, here the microphone is not predicted, but in the gap version it does. And we can see also from the test mean square errors that indeed SVG with the gap algorithm, and with this one, reach lower error than SVG on both bare robots dataset and RoboNet. But as a final note, it's very important to say that though the solution is very neat and it addresses real problems with model-based reinforcement learning algorithm, it does not work in a highly dynamic scene with significant background motion. This is because we are computing the residual on a pixel level. But if the background changes a lot, for example, the camera is dynamic, then also this residual will not be biased toward a zero solution. So this model probably won't work. Okay, this is everything for today. If you liked the video, leave me a like and subscribe. See you on the next one. Bye.